housekeeping there. We are recording this, so please mind your P's and Q's. Not that I need to say that, as we are a fabulous professional organization here, but we are doing that, and there have been a couple of people have ahead of time said, yes, we'd like you to record it, or we'd like to see a recording, because they can't make it. So over to you, Steve.
All right, thanks, Michael. Appreciate that. And for setting up the whole WebEx and doing all the logistics. A couple months ago, I came across an aviation article sent to me by some friends at the Georgia Center of Aviation Innovation about a relatively new space antenna company in the Cherokee County area. That's just north of the Atlanta area and just a little west of me. The company was founded by Dave Horton and Tim Morton. The company is called NXT Communications, or NXTCOMM. The news article reported the opening of their new production facility in Cherokee County, and it described their design work in collaboration with Georgia Tech's Research Institute on something called fragmented aperture technology, as we will learn shortly. Our speaker this afternoon, NXTCOMM's CTO, Carl Novello, joining us from his home in Orange County, California. Carl's relatively new to NXTCOMM, but not to our industry. He brings over 2 decades of experience in satellite communications, systems, and RF antenna design. He's worked with companies like Aris, Panasonic's Maritime Group, Kymeta, and Intellian Technologies, where he led the development of Intellian's Maritime VSAT antenna system. Now that's important. That system won Satellite Technology of the Year award that was presented during Satellite 2019, as some of you may recall. Please join me in welcoming Carl Novello to our SSPI Southeast, socially distanced, virtually connected, masked up, and spaced out Wednesday webinar. Carl, thanks for being with us, and hopefully the screen is yours.
Thank you very much for the introduction, and thank you all for attending. You have me at a bit of a disadvantage. I like to stand up and pace anytime I talk, so this is going to be a bit difficult for me. Not only can I not talk with my hands, I can't pace. So, what we're going to talk about today is a little bit satellite antenna technology in general, in particular focusing on the flat panels, and how a historical retrospective of it is actually shaping our future. So on the topic of history, what industry owes its beginnings to an Austrian supermodel and a sci-fi writer? Well, the sci-fi writer is relatively well known, right? One of the founders of our industry, Arthur C. Clarke. Not only was he a sci-fi writer, but he was also a noted physicist in his own right. Possibly, this is his best known work, 2001: A Space Odyssey. But is it his best work? Is it his most important work? Debatably not. In my humble opinion, and as a foundation for our industry, this piece from October 1945's Wireless World in the UK, Extraterrestrial Relays, asking an important question. Can rocket stations provide worldwide radio coverage? Think about this for a second in the context of the history. Rockets. What do we know? Well, unfortunately, Mr. Clarke, or Dr. Clarke, was in England at the time of World War II, where literally the island was being terrorized by this newfangled technology of rockets, right? And it takes a pretty significant leap of imagination to go, how does this weapon of war give me the ability to do something enabling and beneficial? And this is the backdrop that founded our industry. If you guys haven't, I suggest you read it. It's a fantastic article where he posits the geostationary arc, and that putting 3 radio stations, if you will, or radio repeaters in space in a particular orbit, we now refer to as the Clarke orbit, would keep them fixed with reference to the rotation of the Earth. and provide us the ability to make things like phone calls. Incredible. But also, the Austrian supermodel, Miss Hedy Lamarr, billed as the most beautiful woman in the world. Many people know her from her movie and acting career, but how many people know that she was one of the founders, if you will, of a spread spectrum technique that we use today? If it wasn't for Miss Lamarr, not only would satellite communications to disadvantaged antennas be even more difficult, but little things like mobile phones and Bluetooth and even Wi-Fi possibly wouldn't exist. Because this particular innovation, built from the perspective or iterated from the perspective of, hey, how do we keep people safer, right? Again, backdrop of World War II, is now an instrumental part of our modern day communication methods. So our industry is an industry that was founded by free thinkers, by creatives, by people who could wonder, who could suspend disbelief and say, what if? What about now? In the early years, our industry had unbridled imagination. But have we lost our imagination now? Are those of us who've made our living over the last couple to several decades getting stale? Have we really reached the limits of our own imagination and maybe capabilities? Is that why maybe we're providing fertile fodder to the likes of the new space guys? Are we the same ones who carried on the traditions of Arthur C. Clarke, the dinosaurs now? Lots of money and lots of interest has gone into this new crop of LEOs, right? From Starlink to OneWeb to Telesat and even Amazon getting in on the game. But one of the things that jumps out is, with very few exceptions, none of these are established or legacy providers, if you will, in the satellite industry. They see a need to connect the globe even more ubiquitously than it's been connected today. And what is that need? Well, that need stems from our own addiction of connectivity. Things like this, a Zoom meeting covering people from around the United States, well, I'd say with a varied degree of interest even. What we've learned in the pandemic is even in terrestrial connectivity, sometimes there isn't enough bandwidth, right? So this need is not going to decrease. The need for better connectivity is not going to go away. And it's a little bit interesting that we've had to look to the outside actors in order to certainly spear investment and possibly innovation into this area. So where does that leave us? When we're talking about the existing industry versus the new actors, is this a case of Fred Flintstone meets George Jetson? Are we still relevant? Will we be swept up in the tide of the future? Or will we have a fate similar to that of the dinosaurs? Unfortunately, smothered under our own weight, unable to make new headways. Not all is lost. Because in order to unlock the potential of connectivity, there are a number of challenges that these companies, and us more importantly as an industry, have to overcome. None of these challenges are easy. Potentially, they're not as hard or as daunting as Arthur C. Clarke sitting at his desk conceptualizing an orbit at 22,000 miles away, but they're still difficult. And for the LEO connectivity to work, there's a number of core challenges to meet. The first one is a startlingly simple but poignant one. What we have on the right is a good old-fashioned parabolic antenna represented. In a LEO constellation, you have to be able to track, target, and communicate with satellites that are moving. And since they're moving, you have to communicate with multiple targets in order to make the handoff. That's impractical. That's infeasible in a parabolic antenna. One of the ways you can do this is through the lens or the approach of a flat panel antenna, a phased array, where there are no moving parts and the beam itself is being steered. So that then you can maintain the connection to this satellite, right? And then hand over to the next. That's a challenge still. The next challenge is one that we don't often think of among those that I like to refer to, myself included, the satellite dinosaurs. The definition of the word high performance. To talk about a historical perspective for a bit. Not so many years ago, 128 kilobit satellite connection was considered broadband or high speed. How many of you would be happy with 128 kilobit connection today? I have a 15-year-old son. He was absolutely taken aback. Hey, Dad, what do you mean? I never had to deal with kilobits in my life. And it was an interesting point of reflection. In 15 years, we've really moved away from measuring in baud, right? And moving into megabits and gigabits. This is even more important when you're talking about connecting millions of users, millions of terminals, millions of endpoints. The user experience becomes even more and more important. Even today, how many of us expect a connection in the megabits from our mobile phones? All of us do. And yet, this level of connection in the satellite industry is one that we often make excuses. Oh, well, it's satellite, it's expensive. Oh, well, we can't do that. Oh, well, our customers don't have the willingness to pay. But this is a very real challenge to overcome. Also, another very real practical challenge is the ease of installation. What we see here in the picture on the right-hand side are 3 antennas today, mechanically steered, in order to communicate with a non-geostationary satellite. Granted, this is a perfect solution for a ground station or a teleport or a fixed large enterprise location. But that's not an easy solution to scale into the millions for the masses, right? Likewise, on the left-hand side, you see a typical rack. It still takes a lot of equipment to demodulate these signals and make it to something useful. How many of us would have internet at home if you had to take half of a 48 rack unit rack and populate it in your closet at the cost of tens of thousands, if not more dollars? And in this particular case, over 200 pounds. So in order to unlock these potential, you have to have a solution that's easy to install, that's easy to build, that's easy to distribute, and easy to sell. And when I say easy to sell, it really is a nice way of saying it's got to be cheap. It's got to be built to enable the price points, right? So now, let's talk a little bit about a history of NXTCOMM. A little bit later, after the Wright brothers were spending some time in Kitty Hawk playing around with the early versions of aerodynamics, right? NXTCOMM was founded shortly after, about 2 odd years ago now. And NXTCOMM was founded from a position of industry insiders, if you will, people who had lived in the satellite industry, the same ones that have seen the transition for the last 20 years, asking a question, isn't there a better way of doing this? ignoring all of the excuses that we often give in satellite. Oh, antennas are small, they're expensive, it's moving, it's complicated, satellites are hefty, the cost per month is expensive, and so on and so forth. It just started from the question, isn't there a better way? NXTCOMM, one of the areas that the founders of NXTCOMM were quite interested in, because of, again, history and where they came from, was that of aviation. So from the, is there a better way of doing things, they focused on the discrete problem of, how do I make a better system on board an aircraft in order to provide more reliable, greater throughput, better performing, higher customer satisfaction VSAT services? And after an exhaustive bit of research, the answer showed the antenna is a primary culprit in one of the areas that needed to get better and iterate. So from there came the NXTCOMM vision, the mission of building an extensive network of all types of cloud-driven IoT connected terminals. But how do you get there? How do you go from a vision of connecting all of these things with expertise and experience in the aviation and knowing all of the questions to ask on what can I do to make, or how do I start making something better? You still need technology. And that's where the partnership with Georgia Tech Research Institute came from. As I'm sure you're all well aware, it's one of the primary engineering and research institutions in the country, if not the world. Here, following my historical theme, here are some older pictures of the campus in Atlanta when there wasn't much of a downtown Atlanta from these. But on a research side, they're arranged, if you will, into a number of labs. From advanced concepts to the aerospace and transportation, applied systems, all the way down to sensors and electromagnetic applications. So the founders of NXTCOMM started speaking with some of the folk at GTRI, who they'd known from past lives, and started asking questions. From a relationship with the head of the Advanced Concepts Laboratory came this: Georgia Tech's fragmented aperture technology, which instead of focusing on the back of the antenna, if you will, or what's behind the phased array, their focus was, how do you make radiating elements better, the portion that actually faces the satellite? And through their areas of expertise, they've developed a very interesting computational model that they refer to as a genetic algorithm. And genetic why? One, because it does automatically go through its own process of natural selection to find the best fit for the particular challenge or constraints that are inputted. And then it's self-learning. It iterates from there until something is created. And what you see on the bottom and the top here is an interesting fragmented aperture radiating elements. The benefits here is it's inherently wideband, and by wideband I mean we can design an antenna using a fragmented aperture that goes from 10 gigahertz to 15 gigahertz entirely, so that there's no longer this question of what's my dynamic bandwidth and what's my instantaneous bandwidth. At any given time, your entire antenna can see the entire specified frequency range. And one of the other big benefits to this approach, it allows you higher aperture efficiency. So let's compare. What you see on your right-hand side is a typical or stereotypical iron cross radiator. Oftentimes when we look at flat panel antennas, the radiators themselves are monolithic copper, either a square, a circle of some sort. If you're really cutting edge, they look like a double-ended diamond. Instead, core to the fragmented aperture is this complex pattern that's created from the genetic algorithm. We input a set of variables, what we refer to as the degrees of freedom. There's over 1,000 of them. And this is how we set the goals for the performance of the antenna. We can set goals and constraints. So by taking this approach, you'll notice there's less copper on the radiator. And why do you do that? Well, you do that because you can increase the mutual coupling while decreasing the parasitic coupling. When I look at a traditional radiator here, depending on where you are on this piece of printed copper, if you can see my arrow, this part here is actually, call it stealing gain from the portion right next to it. While this is important from the overall efficiency of the antenna, this parasitic coupling can also have undesired effects resulting in grating lobes. And what these grating lobes do is these two little parts interfere with each other, and that can even be transmitted towards the satellite and it's noticed in an increase of your side lobes, or the undesirable radiation outside of your main lobe being projected towards the geostationary or non-geostationary arc. And by using this kooky little pattern that I like to refer to as the Space Invader, we can maximize performance, not just gain, but also side lobe and regulatory performance, and make better use of all of the space on a radiator perspective, but also on the full buildup of the antenna. Here's our approach. You can see the pattern in each one of the 4 quadrants, and even smaller than that. One of those quadrants is what we refer to as the subarray. And then subarrays can be put together in multiples in order to meet other product requirements. So this is a rough concept sketch of one of our antennas. So the innovation here is in the radiating element. By doing this, we're decreasing the losses. If you decrease the losses, you can increase the gain. Like I mentioned, this design is for the entire Ku band frequency range from 10 gigahertz to nearly 15 gigahertz. The other benefit here, which is critical in phased arrays, and in particular in difficult use cases like aeronautical, you can reduce the power consumption. And if you reduce power consumption, the flip side of that coin is you're reducing the dissipation of heat. So this gives you a little bit of an overview on what we're looking at in terms of a 50 centimeter square, in terms of G to T and EIRP over scan angle. And at 0, meaning the satellite is directly overhead or bore sight from the panel, we have a G to T of 11.9. And then that rolls off in a cosine theta of 1.2 accordingly. So overall, a relatively high performing antenna. And when I look at it from an aperture efficiency as a percentage for a 50 by 50, that puts me in the high 80s, low 90s, depending on where in the frequency band. The important point to note here, because I guess my reference, you can't see it against the black background, that this G to T is at 10.7 gigahertz, and the EIRP is measured at 13.75. So the unfavorable part of the Ku band, instead of what we're used to seeing when we look at EIRPs and G to Ts on the spec sheet at midband, right? A more favorable portion of the frequency. So, core to our solution here is the subarray. A single subarray is the basic NXTCOMM Lego building block. And from there, you can tile or snap together multiple subarrays to meet a particular G to T or EIRP requirement that you have. And this allows us to quickly iterate into new product variants without the time it takes to do this from scratch, right? One of the important design criteria that we inputted in the design of this antenna was that we needed to be modular to a large number of panels, of subarrays. So given this modularity, we can meet a wide range of use cases, whether it's a single 10-inch by 10-inch panel, 25 centimeter, right? Mounted on the roof of an oh-so-pretty vehicle, for example, or a number of them under the standard radome of an airplane, or several of them put together in a quick deploy auto acquire, or an even larger number of them tiled over the top deck of a boat. This allows us to scale to remain modular. Now, it is a bit of a crawl, walk, run approach in terms of NXTCOMM's product development. There's value in the increased performance, and as such, we're looking at first articles in the market on the higher value markets, such as aviation, military, and so on. And of course, as you guys saw before, that fits well with not only our experience, but also the area of expertise of our partners at Georgia Tech Research Institute. So we're rapidly in a phase right now. It's been a bit of a busy time for us, as we will be testing over the air in our first articles later next month. So as you guys can all appreciate, it's been busy. But along the way, we've learned a lot of lessons. This isn't easy. Even though we've been able to leverage a technology that was well developed by Georgia Tech previously, right? Albeit in slightly related or similar use cases. The fragmented aperture, I may have forgotten to mention this, was born out of some work that Georgia Tech did in order to develop very high bandwidth on the order of 33 to 1, 100 to 1 bandwidths for synthetic aperture radar projects for the US government. So well-proven technology that's been fielded, but as you all know, there's always a challenge taking a technology building block that has been used for defense applications and turning the crank to make the sausage to turn that into a commercial product. So tactically speaking, we've had a number of challenges along the way. Thankfully, they haven't had to do with the invention or the core technology, but rather the practical sausage making of building a product. The first one that we had to deal with early on from a design perspective was driving out the cost. In these fragmented apertures that are flying today, right, they are virtually, the money is no object product. So things like finding manufacturing methods to do these things that didn't require esoteric machining or multiple processes or multiple PCBs integrated together and so on. First part, driving out the cost. The second one, the actual manufacture of the circuit boards. And then the last one is completely practical. Power supplies, their size, and how do you distribute power on a board level. All practical considerations don't seem so challenging, but part of the sausage making, and these have been our biggest hurdles along the way. So, as we iterate, this product will be a key component in the global connectivity platform, right? Because we can all see LEO's coming online. You need an antenna that is inherently capable of tracking multiple targets. You need an antenna from the technology perspective that is able to deal with all of the different possible frequency ranges, right? As we know, we think of the Ku band as a monolithic frequency range, but really it's still split up into 3 ITU bands. So our antenna needs to work among all of those. Right? And then the next part of it is, of course, how do you layer the smarts in the antenna itself to enable your customer or the satellite operators or the service providers to really get something that looks like a smart antenna? Today, it's very, very difficult to seamlessly manage an antenna in band. And that's the other part of the NXTCOMM story, that we have a team of software folks who are dedicated to doing this, solving this challenge. As I talked about our products in the aeronautical use space, I thought it was nice to end on something like this that shows the key benefits of the approach. What you have here is a standard ARINC 791 radome footprint that shows a number of our subarrays fitting in the footprint, right, which allows you to maximize the real estate. One of the issues with the mechanical antenna that fits in here today is that even though the reflector is relatively small, the swept volume of the radome has to be significantly larger to accommodate the motion. We don't have such problems with flat panels. So what we can do is we can, again, maximize the real estate. Just like making the crazy space invader lets us maximize the real estate of the radiating element, the tiling approach can allow us the same benefit under the radome. Right? And of course, from a practical commercial perspective, it's designed as an easy drop-in replacement to what's flying today. So when I showed you the NXTCOMM MAX antenna, one of the things that's important to note is the entire antenna is built on a printed circuit board. The radiating elements etched on the top layer, the layer closest to the satellite, and all of the control elements and beamformers as surface mounts on the back. So inherently scalable and relatively low cost to manufacture because it can be printed in any circuit board shop virtually in the world. And this is our approach to how do we help enable the future scale markets. So I thank you all for listening. If there are questions, comments, suggestions, or complaints, I'm all ears.
Wow, thanks, Carl. Everybody can unmute and applaud.
The
That
best
was
part about Zoom meetings is you can't throw anything at me, so that's great.
well, that is an advantage. Hey, Carl, I've got some questions that have come in on the chats. Let me scroll up here. The first, you know, you talked about KU as maybe a primary target that you're working with. You have plans to also, and does the technology also work in a KU band spectrum?
Oh, okay. Sorry, I was remiss in this because I've got KU on the brain because I'm under deadline for over-the-air testing in a few weeks.
Right.
The technology itself is very well suited from about 6 gigahertz and practically 9 gigahertz on up to the terahertz. So one of the important key determinants of the fragmented aperture, of selecting the fragmented aperture as our cornerstone technology, if you will, is exactly that, is the applicability to wide ranges of frequency, right? And from a development perspective, our Ka band development lags our Ku by about 6 months. So in our roadmap today is Ku to Ka, and when I'm talking about Ka, I'm talking about the universal Ka band from 17.3 gigahertz and receive all the way up to 31 gigahertz and transmit. But about 6 months away.
Another question. Can you get the price down to consumer levels, meaning low hundreds of dollars, or is this just for my rich friends with their business jets?
Well, in the initial offering to the market, it will be at a higher price point. But again, from our criteria and deciding which horse to back, if you will, on the proverbial technology side of this, one of the things that we're most keen about in terms of both the fragmented aperture and phased arrays as phased arrays themselves is a point I was making previously about building these on a PCB, right? If you can get to the point where you can enable the scale, then we expect you can enable the consumer price points as well. It's going to take some time, right? But when those volumes increase, we can get there. One of the mistakes that a number of other antenna undertakings have made, unfortunately, is understanding the realistic scale. And by scale, I mean the ramp up time to enable this. Until the LEOs come online, right? Until the new space actors come online with a value proposition that enables the millions and millions of users, right? You won't have the ability to get there until in price point. It's a little bit of a chicken and egg point. So that's why our approach is start with the high value markets that can benefit today, take those lessons learned, and move into the scale markets step by step.
Do you have some thoughts about what your next markets might be? You've talked a lot about aviation. One of the questions from an attendee was, what other markets will you be taking it to besides aviation?
So if you looked at initial markets, there'll be the aviation and the defense related market. Within the defense related market, there are a number of interesting use cases and very diverse use cases, right? When we talk about defense, it goes from airborne platforms all the way down to the in the field or special ops use cases. And that's, again, one of the drivers for the modularity and building this all around a subarray, right? So you can have one piece of antenna Lego that scales up or scales down to meet all of those different, whether it's in a special operator's backpack, right? Or on a C-130 tiled all the way on top of the fuselage. So,
in terms of your market, are you looking at, and this was a question from Bob Castro, I think, Starlink and other LEO providers as being potential customers?
So I get to answer this as the CTO, right? I'm the techie. To me, anybody's a potential customer, right? Potential customer to me means, hey, more money so I can continue my spending spree.
Right, right. Here's another question I think is pertinent. Are you constrained by the ARINC 791 radome, or can you use larger footprints, PCB pieces, and maybe get different yield, a better yield, perhaps?
Yeah, possibly. The 791 radome is quite large. It's nearly 2 meters end to end, and 1.2 or 1.4 at its widest point. So in that real estate, we can actually fit 34 subarrays. So that can give you performance rivaling a terrestrial 1 meter, 1.2 meter parabolic today. So that gives you a lot of room. One of the things that is also core in the fragmented approach, right? Because not only is it the result of the radiator and the pattern, but it's also the math behind it. The technology does not need to be conformal. So what that means is I can have panels not just clicked up together in the flat orientation, but curve around. So from that perspective, maybe the shape of a 791 radome is an anachronism. Maybe instead of a radome like we think of it, 2 meters by 1.5 meters nearly wide, maybe that gets replaced by something that's 50 centimeters long, wide, right? And down the entire length of the top side.
Right.
Or the other side is, hey, maybe it's something that's 8 subarrays wide and conforms to the fuselage.
All right. This is a question. I actually have a couple related questions here. And in terms of the beam, you showed, I think in some of the sketches, it looks like there are multiple beams. Can you do multiple beams? And then kind of related to that, talk a little bit about the power requirements. I know that goes up and down as you switch satellites, switching from the one above to the one ascending and so forth. Tell me a little bit more about the support for multiple beams and how you handle the power as the satellites are moving across the sky.
Yeah. So first things first, support for multiple beams. Yes, that's inherent in all of our designs, even this initial one, right? Because we feel that's the reality, and that's something, if you don't have it today, you don't have a product for the future. So yes, we support the transmit and receive to multiple satellites simultaneously.
On the power side, does that reflect in up and down of the power and transmit power in particular as you're going from one satellite to the other?
It does, but it's relatively small, right? Because of the way we designed the beam forming and the software that controls the beam forming, right? How do I put this? Targeting 2 satellites does not provide a max power difference than targeting 1 satellite. So the variability is in the nominal power, and that's relatively low.
Another good question popped in. Why has the antenna been such a tough problem to solve? Where has the industry gone wrong before now? You talked a little bit to that, but what are some other areas where we've tried to solve these problems and perhaps went down the wrong roads?
So the antenna is it's a hard challenge. It really is a hard challenge. And when we look at it, a number of we've tried before in the industry to solve the antenna problem by inventing something brand new. Invention is always hard. It's that old joke about, sorry, boss, my invention can't be scheduled. And that's very, very difficult. So whether we're talking about using different materials, whether they're frequency selectable surfaces, or whether we're talking about the metamaterials to remove the phase shifter, and so on and so forth, that invention is hard. Whereas what I like about the phased array is that fundamentally, a phased array relies on integrated circuits, and if it relies on integrated circuits, then there's this whole other world of ICs around in other uses that I can draw from, right? That I can learn from, that I can iterate from. So in my view, one of the problems is people have looked too hard to do something new on the antenna side instead of, hey, how do we take something that's well proven and innovate on it? As in the classical sense of innovation, make something better, not make something brand new. So that's one part of the problem. The next part of the problem is quite frankly the vulgar part. Look at how much money has been invested in new space. Billions of dollars have been committed to brand new satellites. And nowhere near that has gone into the development of antennas. even the examples of the best financed new antenna ideas in our industry, right, aren't even to the point of half of the cost of buying a new satellite today. And that's their lifetime investments.
Good point. And on a related note, another question. So these problems in the past, what disruptions in SATCOM do you see are needed to get to a market kind of similar to the cell market back in the 80s? What disruptions do you think are needed? How likely are they?
Well, I think when you point out the cellular markets in the 80s, I think we're going to see the same classic or the same type of disruptors that market saw. First and foremost, they saw the disruptor of standardization in Europe, right? The concept of roaming, of GSM roaming, was probably the single biggest disruptor to the cellular markets because it made everybody play to the same standard on the basic RF level, right? And we're going to need that. And the second thing that changed was the scope of the operators. I mean, I remember a time when cellular providers, the network owners themselves, the guys who activated and turned on your phones, were not big telcos, right? So the companies themselves have to scale. The service providers themselves have to scale. And that's a big potential for disruption, because that also intimates that the distribution model and the business model has to scale. And that's going back to are we the Jetsons or are we the Flintstones? Where it's a terrible thing to ask, and hey, as the techie guy, I don't care, but what happens to the existing groups of satellite service providers? Do they have the scale to garner the volumes that the likes of a OneWeb or an Amazon think that they can? You know, one of the simple things, when we talk about mobile phones today, how many phone calls does it take you to activate your mobile phone or buy your mobile phone? None. You buy the thing on Amazon or from your carrier's web store or from Apple or whomever. You get it sent to you in the day or two. You open it up, you take it out of the box. If you don't do it on the handset, maybe you go to a website and put in an ESN when it doesn't work, and off you go. Anybody try to activate a satellite service in the last 6 months? Even the most user-friendly of it is a nightmare. Try buying satellite services, even from the most user-friendly guys, the guys that do it really, really well. It's not the same level of seamless as it is for a mobile phone today. And those are some of the process disruptions we have to undertake. And it's a question, do we disrupt ourselves or do we get disrupted by somebody else? From that particular focus, that's why I find Amazon to have the largest potential for disruption.
Right. Got time for maybe one last question. And you mentioned that you're focused on high value markets. Can you elaborate on where those are?
Let me be clear what I mean by high value. When I'm talking high value, I don't mean the guys with the proverbial pile of cash. I mean the markets where our product provides a highly differentiated value, right? Those markets where higher gain, the form factor, and the modularity are really key selling points. And I see those in two primary areas starting out, right? One, of course, is the aero market, and then, of course, the variety of different defense-related use cases. But as that progresses, right, and as we learn lessons and the new LEOs come online and so on and so forth, then we'll see that move into other things like the enterprises, potentially on a land mobile perspective for, say, high value transport, right? and then moving down further down into the market pyramid where you get into the millions of users as things progress.
Well, Carl, I think we're coming up to the end of the hour, and I would like to get everybody to unmute again and provide a polite round of applause. This is really fascinating technology, and we're very grateful that you could join us and dig into that a little bit this afternoon.
My pleasure.
Thanks everybody also for attending and all the good questions that we had. That was awesome. Michael, I see you're still there with us.
I am.
In the few minutes that we have left, I would like to ask you to tell us about what we have coming up for SSPI Southeast.
That would be my pleasure, Steve, and thank you, Carl, for the presentation. I would say, I mean, we part of what SSPI does in the Southeast chapter is the networking part of what we do. When pre-COVID, when we used to be able to meet in person, that was one of the fun things that we could do in person, is network and go up and speak to people you haven't seen for years at one of our meetings in person, or people you're sick of seeing because they're there at the meeting all the time. Who knows? But networking is good fun. So we don't shut the Zoom down right at the end. So if whatever conversation or questions for other people in the audience, please have at it, as it were. And I'd also encourage you, we still have as I say, we don't really have a time limit. Anybody wants to ask Carl a question in person, I'll give you a minute to think about it, because I have a couple of things to talk about here. And we mustn't forget the gift card drawing, which, Steve, I will send the winning person's name to you via chat for you to announce. Let's have a look here at this number. Oh, I have, it looks like this person is an Airbus employee, or at least their email says airbus.com. Chris Schaupman.
Yeah, can you hear me?
Yes.
Yeah.
Loud
Yeah,
and
hello.
clear. Loud
Thank
and
you.
clear.
That's lucky me. It's very late here. It's kind of 12:30 in Germany. And yeah, thank you for the presentation. So I won $50, is that correct?
Okay, foreign exchange rates, we may have to have a committee meeting to discuss that. But
No, don't worry. I donate that for the SSPI Southwest chapter. So please take that as spend the money on my behalf, and thank you so much for organizing the call.
Oh, well,
Thank you.
very good. When you said Southwest, did you mean Southeast?
Oh, sorry, Southeast.
I have a question, but it's kind of like a small question. It's not really like on a big scale. In the beginning, when you were talking about, like, somebody was talking about like a woman that was like revolutionary to satellite communication. Can you say her name again? Because I never got it. It was
Hedy Lamarr.
Oh, thank you.
HEDDYLAMARR.
Okay, thank you.
Welcome.
Thank you, everybody. And we'll get the info out about the future programs. Another round of applause for our presenter, Carl, and to NXTCOMM.
Excellent,
And,
bravo.
Go, Carl.
Thanks, guys.
Thank you.